everybody, welcome to the light science demonstration. I'm Michelle, and I'll be doing the demo for you. Now before we talk about light, we need to talk about how we see, or rather how people used to think we saw. Way back during the time of the ancient Greeks, they thought we saw things because our eyes shot magic rays out of them. These magic rays would travel out of our eyes, hit an object, bounce off, and come straight back into our eye, and that's how we saw our surroundings. But they never tested that theory, and in science you should always test your theories. So we've created a little bit of a test. Alright, so what's going to happen is I'm going to come on over to you. You're going to take a look through this box and you're going to let me see, tell me if you see anything in this box. As you can see, can't really see anything inside. That's because our eyes don't work using magic rays. They work via light. When you allow light in, you'll be able to see, but it was a rubber ducky the entire time. Our eyes require light. Without light, there is no sight. What happens is light will hit an object, bounce off of it, and enter our eye through our pupil. That is the dark circle in the center of our eye. It acts like a hole. The amount of light that gets let through our eye is controlled by our iris. That's the colored part of your eye. If someone says, oh, they've got brown eyes, green eyes, blue eyes, they're referring to the iris. After it goes in through the pupil, it'll hit the lens. The lens is what allows things to focus, kind of like the lens on a camera does. After it's focused through the lens, it'll hit the back of the eye where the rods and cones will pick up on how dim or bright the light is and what colors it is. And then that information will be sent through our optic nerve to our brain. Now it's very important to note our brain is receiving two pieces of information, one from each eye. Our brain will then take both images, merge them together into one, and then flip it upside down. Turns out our eyes are actually seeing things upside down. It's our brain that flips them right side up. Alright, so that is how we see. But let's talk a little bit about color. For example, there are lights shining down on me. And I'm sure normally in your day-to-day life you have lights on you as well. Do you know what color those lights actually are? Many of you will say white or a yellowish white depending on the type of lights. But it's actually not white. Let me show you. This projector screen also gives off white light. However, I can break that white light up into all of its actual colors using something known as a prism. And using that prism, you can see white light is actually a rainbow. White light is actually red, orange, yellow, green, blue, indigo, and violet light all shining at the exact same time. And because they're all shining at the exact same time, when that information gets to our brain goes, oh look, the color white. But in science we can actually call it Roy-G-Biv light, the first letter of each color. Now, what does it mean that we have all these colors of light shining down at us all at once? Well, that's how things appear in color to us. Whenever you see something that is in color, it is in color because of the way the colors of light are interacting with it. Let me show you over here. I have 4 color panels. I have red, yellow, green, and blue. Now, we see this as the color red because that Roy-G-Biv light is hitting it. The orange light, the yellow light, the green light, the blue light, the indigo light, and the violet light are all being absorbed. They're all turning into heat energy. The red light, on the other hand, is bouncing off of this panel and coming right back at us, which is why we see this as the color red. For the yellow panel, the red, the orange, the green, the blue, the indigo, and violet light are being absorbed, but the yellow light is bouncing back at us. This is green because the green light is bouncing back at us. This is blue because the blue light is bouncing back at us. So take some time to look at all the colors in the room around you. They are the colors that they are because the color already exists in the light shining down on you. Now that's well and good if you are using white light, but what happens if you change the color of light? Well, let's find out. This is just a little flashlight, and right now I have some white light shining on here, so all the colors look the same. But I happen to have a red color filter. When I use this, I will turn white light into mostly red light. I say mostly because a few orange and yellow light might leak through, but for the most part, all the other colors are going to be blocked. So, white light, red light, white light, red light. You may notice a few of our colors have disappeared. Red still appears red because red light is still hitting it and being reflected off. Our yellow looks a bit more orangey red at the moment. Like I said, this is not a perfect red filter, so some yellow and orange is leaking through, which is causing that to be a slightly different color. You'll notice our green and blue are black. That is because green and blue pigments will absorb the red light. And because they absorb the red light, no light is bouncing off of them, which means to us, the color appears black. Okay, that's important to remember. Black, the color black, happens because no light is being reflected off of that object. So if you are wearing a black t-shirt or shoes, it appears black because all the colors are being absorbed. That's also why in the summer, you shouldn't really wear black colored clothing because all of that absorbed light turns into heat and it makes you really hot. The opposite is white. If you are wearing a white t-shirt, it is reflecting all the colors back at you and it's not absorbing any of them as heat. All right. So now that we know where the colors come from, we're going to switch over to art class, I guess you could say. In art, I'm sure you have all mixed colors before. So, I have a yellow panel and a blue panel. The yellow is yellow because it is reflecting the yellow light but absorbing all the others. This is blue because it is reflecting the blue but absorbing all the other colors. When you mix yellow and blue together, what color do you normally get? Yeah, you normally get green. You end up with green because you have mixed the two colors together. So the yellow part is still reflecting yellow and absorbing all the colors, including blue. The blue is still reflecting blue, but absorbing all the colors, including yellow. So by mixing them together, we have subtracted some of the yellow and blue light from each other, and we've gotten this green. So in art class, you are doing what is called subtractive mixing. You start with white light, and you take away some of it to get the color you need. This is also how a printer works, or a color printer works. So I have here this lovely little picture with some swans and a nice building. And this came out of a color printer. But a color printer does not actually print in all the colors you see here. A printer only prints in 4 colors. It prints in yellow, it prints in magenta, it prints in cyan, and it prints in black. Using that subtractive mixing, however, we can get all the other colors we need. So your printer will usually lay down everything in yellow first. And then it'll add some of that magenta on top. You can see using that subtractive mixing, we've already got some new colors happening. Lay the cyan on top of that. We've got some more colors in there, and adding black brings everything out in sharp detail. And we have our original photograph. Okay, so this is all that subtractive mixing. Light, however, doesn't work using subtractive mixing because you can mix different colors of light together. Let me show you. What we're going to need right now, though, are the lights off. So, here we go. So I have a box here. It has red light. It has blue light. And it has green light. Now normally in art class, if you mix red and blue together, what color do you get? Yeah, normally you get a purple, but with light, you end up with more of a pink. If you were to mix green and red together in art, you normally end up with a terrible brownish color, but with colors of light, you get yellow. And if you mix all three of these colors together in art class with paint, you're going to end up with a black or a brown, but here with these lights, you get white light. That's because when you're mixing colors of light together, you are doing what we call additive mixing. You are starting with no light, and you are adding colors until you get to white. This has to do with the fact that our eye sees in three different colors. You have the primary colors of art, red, blue, and yellow. We have primary colors of light, red, blue, and green. When we see a green light, those green receptors in our eyes fire off and it tells our brain, hey look, that's green. Blue tells our blue color receptors, they fire off, look, blue. When all three are going off, our brain interprets that as the color white. We can actually see it really well with my little light ball of science. There are three color LEDs in this light. There's a green, a blue, and a red. When it's staying still, it all appears to be white. But if we get this in motion, you should be able to see all the different colors. Ready? Because we've separated it out a little bit and added some speed, our eye can see the individual colors right now that are making up this light. So now we know all about colors. Let's talk about the energy in those colors. There was a scientist, Herschel, who wanted to know how much energy each color of light actually had. So what he did was he split up a white light, similarly to what I've just done, and he had some thermometers because light gets absorbed as heat. He put a thermometer in the red light, he put a separate thermometer in the orange, one in the yellow, green, blue, indigo, violet, and he even stuck one across the room in the dark so he would know what room temperature was. Now as he did this experiment, he left them in the light for a couple of hours and he came back to them and he pulled the thermometer from the violet light, saw the temperature, recorded it, pulled the light from the thermometer from the blue light, and noticed something interesting. It was showing a slightly warmer temperature than the violet did. Green showed a warmer temperature than blue. Yellow was warmer than green. Orange was warmer than yellow. And red was the hottest out of all of them. So, if you ever wondered why people refer to red, orange, and yellow as warm colors and green, blue, and purple as cool colors, they actually are, scientifically. Faucets, the red faucet is the hot one because red is a hotter color than blue. So he was very pleased with his discovery, and he went to clean up all the other thermometers because he left a few others out there. He left the one across the room in the dark for room temperature. He also had one, however, in the dark, just beyond the red. And when he went to collect that thermometer, he noticed it was the hottest temperature out of all of them. Hotter than room temperature, hotter than even the red. What he discovered was a color of light we can't see with our eyes. The red, orange, yellow, green, blue, indigo, violet, these are the visible spectrum of light. That's what our eye can see, but there's actually more colors out there that we physically cannot see. And just beyond the red is infrared. You might have heard of infrared before. Infrared, we don't normally see. Normally, we feel it. That's what we usually feel as heat. All right. So I have here a little thermometer. And we're going to shine this white light on the thermometer. Now, with this light bulb, most of the light is given off most of the energy is given off in the visible spectrum. Very little of it is heat. We can see it's moving the needle, but not all that much. I happen to have an infrared bulb, however. Some of the energy is given off as red light, but most of it is given off as infrared, as heat. Let's watch that needle now. We can notice it's moving a lot faster and it's getting a lot hotter than the white light. That's because, again, most of this light is infrared light. It is coming off as heat. We just actually can't see it. This type of light is used sometimes to keep food warm, or if anyone's ever hatched chicken eggs or anything like that, you might have used a heat lamp to keep them nice and warm. Or anybody who keeps reptiles would use something similar to keep them warm. Now, along with there being a light beyond the red, there actually is another color of light below the violet. Does anybody know what that color of light is called? Well, if any of you use sunscreen in the summertime, you'll know it's to protect you from the ultraviolet rays, which is that color of light. This is a UV light. It's also sometimes referred to as a black light. Some of the light is given off as a violet color, but most of it is given off in the UV spectrum. Now, what we're going to do here is we're going to look at some differences of color in white light versus UV. So, first I'm going to start with these. Alright. We have here this color. What color is this, everyone? Yeah, it's a yellow. This right here, what color is that? Orange. And of course, we have green. Now that's what they all look like under a standard white light. But let's see what these colors look like under a UV. That's our yellow again. That's our orange. And that's our green. Not very impressive. Let's try a few other colors. Let's try this. What color is this? Yeah, okay, some of you might be saying neon yellow. What about this one? Like a neon green. And this one? Like a neon orange. All right, let's see how these look under the UV. All right, are you guys ready? Here's our yellow. Here's our green. And here's our orange. Now, many of you would say these are neon, and I even use that to describe these colors, but it turns out these are not neon. Neon is a type of gas, okay? And it is a colorless gas. Neon itself doesn't have any color. People refer to the old neon signs as neon signs because they had that gas inside of them, but the color actually came from a paint that the glass was treated with, not the gas itself. So this is not neon orange. It is fluorescent orange, like the colors on your highlighters. Fluorescent means that they're fluorescent pigments. When UV light hits them, they get excited. And when they get excited, they shine a little brighter. And with that, that is the end of our light demonstration. Thank you all very much for joining me today, and I hope you learned something new or interesting. Bye!